Assalamu alaikum. In this video we will study the Dijkstra algorithm and then we'll implement that in Python. Firstly, Dijkstra is the path search algorithm on a weighted graph. It solves the single source shortest path problem, which means it gives the path having the minimum cost from one starting point, which is known as the source point. What is meant by the cost of a path? To give you an easy to understand example, we use Google Map to find a route between two locations that usually is the shortest path in terms of distance. For example, here I have searched a path between 2 points and the suggested route is of 9.9 km and is the shortest path. At the present there is no traffic congestion and this suggested path is the best path. But suppose if there is some problem on this segment like the blocked traffic, then Google Map will suggest you this path which is not the shortest in terms of length but obviously is the best one. We can say that this suggested path has the minimum cost and the cost is not just the distance but also has the traffic condition included. Similarly, if there is traffic issue on this road, Google Map will suggest this route. So the point is that in terms of best route, the cost generally is the distance and we want to get the route with the shortest distance, but many times it's not just the distance but can be some other factors and the goal is to get the path with overall minimum cost. Let's see what will be the final output we will develop in this lesson. We will generate a random maze of any size. For example, this maze is of size 6 by 6 and this is the start point and this is the goal point. Like the Google Map example, if we will find the path between start and the goal point, the Dijkstra algorithm will give us the shortest path which is of length 10. It is basically this path. We can also visualize the path. Let's do that. And now you can see the suggested path and the total cost is 10. Each cell has a cost of 1 and hence total 10 cells in this path has the cost 10. Now let's change the cost of this cell 44 to some high value like 100 and let's see which path algorithm will find. I'm adding a red color hurdle on cell 44 and the cost of the hurdle is 100. I will test the function with hurdle h1 provided as input argument. You can see a hurdle here and hence the algorithm calculated a different path. The new path is again of cost 10. Let's add another hurdle on this cell 46. Now you can see algorithm calculated the path without hurdles and the total cost is 14 this time. These hurdles do not mean that they will block the path completely. The algorithm can select that in the path when no low cost path is available. So let's add the 3 more hurdles on these 3 cells. Now the algorithm calculated the path having the hurdle because there is no better option and the total cost this time is 110. Another example where the Dijkstra algorithm is used is routing of IP packets between different routers. It uses the open shortest path first protocol that uses the Dijkstra algorithm to find the best path for a packet. There are routing tables in a router and router uses the routing tables to decide the path for the next packet using the Dijkstra algorithm. Before moving further, I would mention that the two examples we discussed, the Google Map and the IP packet routing, both do not just simply use the Dijkstra algorithm, but there is a lot more than that and that's not a topic of the video. So what we will cover in this video is 3 things. First is the Dijkstra algorithm detail on a weighted graph. Then we will implement that algorithm using Python for a weighted graph and then we'll implement the algorithm on a maze to solve the maze with some high cost cells inside it, like the one you saw a while ago. So let's get started. We will consider this weighted graph to study the Dijkstra algorithm. First note that all costs are positive cost or weights and Dijkstra algorithm can give wrong results with the negative weights. For negative weight graphs we use Bellman-Ford algorithm. Now let's see how Dijkstra algorithm will solve this graph. For that we have a start node, for example the node A, and solving this graph means we want to find the cost to reach to each of the node from node A, or it can be to reach to one of the node. For example, to reach to node E from node A, there can be 3 ways shown in 3 colors and the green path is the one with the minimum cost of 5 and that will be calculated by the Dijkstra algorithm. Similarly, to reach to node D, this will be the minimum cost path out of many possible paths from A to D. The working principle of the Dijkstra algorithm is a greedy approach. It starts from the start node and will store the cost to reach to all direct nodes connected with the node A, which are node B, F and C. It does not know the cost to reach to other nodes at present. Out of the 3 nodes B, C and F, it will choose the one with the minimum cost which is B. From B it will check the cost to reach to the connected nodes. Let's just consider the node C. From B we can reach to C with a cost of 6. In first step the algorithm knows the cost to reach to the node C is 9, but now from B it can reach to C with a cost of 6. and cost to reach to B is 2. So following this path we can reach to node C from node A with a cost of 8, which is better than following this path to node C with a cost 9. And so on, the algorithm will keep on selecting the next node with the minimum cost and will check the connected nodes to see if a new better cost path is available. So that's the key working principle of the Dijkstra algorithm. Now let's explore the complete algorithm in detail with the starting node as a node A, and we'll find the shortest path to all other nodes. We just know that the starting node is node A, so the cost to reach to node A is 0 and the cost is infinite for all other nodes. The algorithm will pick the node having the shortest distance from node A, and that at the moment is the node A itself. I'm showing it as A0, which means that we are at node A with the cost 0 and will explore the cost of its connected nodes. Node A cost will remain 0, node B cost is 2, node C cost is 9, and there is no direct path to node D from node A, so the cost of node D will remain infinity. Similarly, infinity for node E, and for node F it will be 4. I will mark the node A as a node that has been visited. Now I will choose the node from the unvisited nodes having the minimum cost, which is node B. Now I will update the cost if I get a better cost from node B. The update is possible only for the unvisited nodes, because the visited nodes are already at their minimum cost since all costs are positive. Node A will remain with the cost 0 since that has already been visited. The B will also remain as 2. From B I can reach to node C with a cost of 6, and the total cost from A will be 6 plus 2 equal to 8. It is better than the previous cost of 9, so I will update that to 8. Now from B we cannot directly reach to node D, so that cost will remain as infinity. From B we can reach to E with the cost 3, and hence the total cost from A to E is 2 plus 3 equal to 5, which is better than infinity, so we will update that. Then from B we can move to F with the cost of 2, and the total cost from A is 2 plus 2 equal to 4, which is same as the previous cost, and we will keep that as 4. So far it means that in 2 iterations the algorithm has found that from node A it can reach to different nodes with these costs. This process will continue. From the unvisited nodes we will choose the one having the minimum cost, and that is node F. We will update the cost. The update is possible only for the nodes directly connected with the selected node, and there is just one node E connected with the node F. The cost from F to E is 3 and cost to reach to F from A is 4, so the total cost will be 3 plus 4 equal to 7. It is higher than the already calculated cost of 5, and we will not update that and will keep that as 5. It simply means to reach to node E from the starting node A, we will not follow this path which is having the total cost of 7 because the previously calculated path gives the better cost of 5. Node F is not directly connected with any other node, so the other costs will remain unchanged. Now F has also been visited. We will choose the unvisited node with the minimum cost, and it is node E. Cost to reach to node E is 5, and with node E there are two directly connected nodes, node C and D. From node E to node C, the cost is 2, and hence the total cost is 5 plus 2 equal to 7. It is less than the previous cost of 8, so we will update this cost. Then from E we can reach to D with a cost of 5, and total cost will be 5 plus 5 equal to 10. It is better than infinity, so we will update that. There is no other node directly connected with D, so the other costs will remain unchanged. We are left with two unvisited nodes, node C and node D, and we will choose C because it has the lesser cost. There is only one node directly connected with node C, and that is node D. Cost from C to D is 1, and hence the total cost from node A to D is 7 plus 1 equal to 8. It is better than the previous cost of 10, and hence we will update that. There is no other unvisited node left, and the cost to the visited nodes will remain unchanged. Now there is just one unvisited node, which is node D. With node D selected, there is no unvisited node left, and hence the cost of the other nodes will remain same. This completes the algorithm, and these are the final shortest costs to reach to each of the node from the starting node A. Now let's implement this algorithm in Python. Firstly, I will define this graph in the program, and I guess a dictionary is the best option, such that a node will be a key of the dictionary and value will be another dictionary describing the directly connected nodes with their cost. For example, for node A, the connected nodes are node B, C and F. A is connected to B with the cost of 2, and it is connected to C with the cost of 9, and connected to F with the cost of 4. Then node B is connected to node C with the cost of 6. B is connected to E with the cost of 3, and to F with the cost of 2. Similarly, the information of other nodes should be added. Now I will create a function. The first argument will be a graph, second will be the start node, and third will be the goal node. We can solve the complete graph or just till the goal node. I will store the collection of unvisited nodes as a dictionary. I will use dictionary comprehension that for all nodes which are the keys of the dictionary graph, the key will be the node and value will be infinity. And then the value of the start node should be set to 0. So this dictionary unvisited corresponds to this information. At the moment all nodes are unvisited, so I'm defining an empty dictionary named as visited. I will implement the algorithm logic and will pick one node from the unvisited dictionary, will update the cost and will put that inside the visited dictionary. So at the end unvisited dictionary will get empty and visited will get the final shortest cost of each node. So I have a while loop till the unvisited has any element, meaning that it is not empty. I will select the minimum cost node from the unvisited dictionary. By default, when min function is applied on a dictionary, the minimum is decided based on the keys of the dictionary, but we want to choose on the basis of the value of the key value pair. For that, we can specify the criteria of selection of the min function by specifying the argument key. Don't confuse this key with the key of the dictionary. This key is an input argument and it specifies the criteria for the min function. We need to provide a function as this argument, and what min function will do that it will apply that function on all elements of the collection which is provided as the first input argument and will return the element that gave the minimum result against that function. On dictionary object, we can apply the function get and that returns the value against the input key of the dictionary. So what effectively this means is that it will apply the function get on all keys of the dictionary and will return the one giving the minimum value, and that's what we want. The first thing is that now that node should be added to the visited dictionary with that cost. Then we need to explore all its directly connected nodes. I'm calling those as neighbors. And I will get that information from the graph. It will return the value which is again a dictionary, and we need to check each node which is the key of that dictionary. Even if we skip this dot keys, it will be the keys by default. So for the connected node, if that node is already inside the visited dictionary, it means its cost is already calculated, so we need to do nothing. Otherwise, we will calculate the cost to reach to the neighbor node from the selected node, which will be this cost to reach to this selected node plus the cost to reach to the neighbor node, and that we will get from the graph dictionary. This corresponds to some of these value dictionaries, and we need the cost corresponding to the neighbor key, so we will specify that. Then we will check if the new cost is less than the already stored cost. If yes, we will update that to this new better cost. This will be done for all connected neighbors. And then outside the for loop, we will remove this node from the unvisited dictionary, because next time we have to select the node with the minimum cost from the remaining unvisited nodes. This completes the algorithm, and at the end the dictionary visited will contain the shortest cost to each of the node of the graph. Let's first check that by printing it. I will provide the start node as node A and goal node as node D. So these are the final costs, and you can verify these are the same as we got earlier. At the moment, goal node does not matter. You can see in our function logic, we have not used the goal node, and hence whatever is the goal node, the algorithm will solve the complete graph. But if we have a goal node, we can stop the process when we have reached that node. Now when I have provided the goal as the node B, you can see it has not solved the complete graph. If goal is D, now it is a complete graph because node D gets visited at the end. Instead of printing the unvisited dictionary, I would like to return the cost to reach to the goal node. It will be better to have the variables for the start and the goal node. So we get the cost value. Next important thing is getting the path information as well along the minimum cost. For example, to reach to node B, the cost is 8, but it will be good to know the exact path as well. I will explain the logic to get the path over here. For simplicity, let's see we want to get the shortest path from A to C. We can store the path as a dictionary. Starting from node A, we will store this information as key value pair with key as node A and a value as node B. Then for the next node C, if we will try to make node A as a key and node C as a value, that will be done. But in dictionary, we cannot have the duplicate keys and the previous key value pair between node A and B will get overwritten. So we cannot save these 3 connected nodes information for node A. There could be a way that we make node A as key and a list of 3 nodes as a value. But even then, when we will move to the next step and will store this information from B to C, then we will have to remove this path from A to C because that is a high cost path. But there is a second better and easy way to find the path, and that is by finding the reverse path from goal to start node, and later we can invert that to get the forward path from start to goal node. For that, starting from the start node, we will store the reverse path information. Node B, C and F are keys and node A is the value. In dictionary, we can have duplicate values, so there is no issue in storing this information as a dictionary. In next step, after we decide that path from B to C will provide a better cost, this information will be stored in the reverse direction, and when we will store this key value pair with key as a node C and the value as node B, with this the previous key value pair with the node C as a key and node A as a value will get overwritten by this new pair. And that is very good for us because that was a path with the high cost and it got deleted by itself. So in this way, if we will save the path, that will be the reverse path from goal to start, and later we will invert that to get the forward path, and let's see that in code. Here I will define an empty dictionary to store the reverse path, and when a new better cost is found, we will add a key value pair with the neighbor as a key and the selected node as a value. So outside the while loop, the complete reverse path will be stored. Let's first check it for the goal as node E. The cost from A to E is 5 and this is the reverse path. How to read this path? We will look for the goal node as a key. It is this one. The path is from node E to node B. Then we will see the pair with the node B as a key. It is this one from B to A. So the overall path is from E to B and then from B to A. Only 2 key value pairs are representing the path from E to A. Of course, we need to make it better readable. For that, I will convert this information into a string of path nodes, still in the reverse direction. The reverse path starts from the reverse path dictionary with the goal node, so I am declaring a variable for that. Then is a string starting from the goal node. Then I will keep finding the next node until I reach the start node. And I will concatenate the next node with the path string. Then the next node until the start node. Let's see what we get. And this is the reverse path from node A to node E. Now we just need to invert that to get the forward path. And we'll return that. Let's check it. And this is the forward path from the start node to goal node. Let's check it for node D. The cost is 8 and this is the path A, B, E, C, D. Let's change the cost from B to E as 13 instead of 3. And now the shortest path is A, B, C, D with the cost of 9. So you can test this code on any graph and will get the correct output. I will change that back to 3 and will put the main code inside the if statement. Now the last part of the video is developing the Dijkstra algorithm to solve a maze that could have some high cost cells. To work on maze, we created a module pyamaze. You can download that as pip install pyamaze, or you can get the code of the module from the description and just keep the file pyamaze in your working folder. There was a detailed video on the use of the module pyamaze, and if you haven't watched that, still you can continue. We have imported the class maze from pyamaze module. Next, we will create a maze object of size 6 rows and 6 columns. Then we will use the create maze function to create the maze. By default, it will be a perfect maze, meaning a single path from start to goal. And loop %100 means there will be multiple paths. Then finally is the run function to run the simulation. This is a random 6 by 6 maze. This is the start cell and this is the goal cell. Also remember, these are the cell indices for each cell. There are few maze parameters you should know in order to implement the next logic. Rows is the number of rows of the maze, which is 6 for this case. Cols is the number of columns of the maze, which is also 6 in this case. Then an important parameter is maze_map. It is the information of the open and close walls of the maze as a dictionary. The keys of the dictionary are the cells, and value is another dictionary with the information in east, west, north and south direction. For example, for cell 11, just the south is 1, which means that is open, and other 3 walls are closed. See here, only south is open. Then we also have the agent class in the module, using which we can place agent on the maze. We will use that to indicate a hurdle or the high cost cell. Let's create one hurdle as an agent. First input argument is the parent maze, which is my maze, and then we have to specify the position of the agent, for example 4, 4. Then we can specify the color of the agent as well, for example red. Another way to specify the color object is by using the color class of the module, and here we can specify that as a color class object red. See, a red color agent is placed at 4, 4. Let's create another agent at 4, 6. Now for these agents there is an attribute position which we can access, and it will return the position of the agent. It is printed as a tuple 4, 4. One advantage of object-oriented programming is that we can assign extra attributes after an object is created if that is allowed by the developer of the class. So to specify the value of the cost for some cell, I can assign a parameter cost to the agent object, and the cell inside which this agent will be placed will be assigned that cost. Now let's make it the main program and write the function for Dijkstra. The first input argument will be a maze, for example m, and then we can have as many hurdles as we wish, so I will specify that with the variable length input argument age. I will follow the same logic we saw a while ago. I will start with the unvisited dictionary. In graph we had nodes, and in a maze we have cells. I forgot to mention earlier that a maze object has one parameter grid, and that is actually a list of the cells inside the grid starting from 1, 1 to last row and last column cell. So for all cells inside the maze grid, I will add a key value pair inside the dictionary with key as cell and the value as infinity, which represents the cost. But for the start cell, which is the last row column cell of the maze, the cost is 0. Then will be an empty dictionary visited. Then the while loop with the condition that unvisited is not empty. I will pick the cell with the minimum cost from the unvisited dictionary. Add that cell with the cost into the visited dictionary. Then we can have a condition if the goal cell is reached, which is the cell 1, 1, we will end the process. Otherwise, we have to check the 4 neighbors or the child cells of the current cell. The 4 cells are on the east, west, north and south of the current cell, so we can have a for loop for the 4 directions. Firstly, we will check if the wall in that direction is open. That we can check for the maze_map parameter for the current cell. The value is also a dictionary, and we will check the wall in the direction D, which is the loop variable. Only if the wall is open, we will find the neighbor cell or the child cell. Child cell will be different for each direction, so I will write 4 if conditions for the 4 direction. If direction is east, child cell is on the right side, so the row index will be same as the current cell, and the column index will be 1 more than that. Likewise, I will write the condition for the other directions. Only one of these 4 if conditions will be true in each iteration. I think it will be better to have else if here. Now when we have found the child cell, we will check if that is already present inside the visited dictionary. If so, we will skip to the next iteration. Otherwise, we will calculate the new cost to reach to that cell, which is the cost to reach to the current cell plus 1, since we need one step to move to the child cell from the current cell. At the moment, let's just ignore the hurdles, and in a while we will add those. Then if the calculated cost is better than the old cost, we will update the cost of the child cell. And then we'll remove the current cell from the unvisited dictionary. This will continue until the goal is reached, and at the end we can return the cost of the goal cell from the visited dictionary. Let's test the function. I'm adding 2 hurdles, although we have not included their effect at the moment. It will return the cost. We can print that cost, but a better way will be displaying that on GUI. For that, I will import the text label class from the pyamaze module. I will create the text label object. First argument is the parent maze, then is the title of the label, and finally is the value, which is the cost returned by the Dijkstra algorithm. Let's check it on one fixed maze rather than a random maze every time. We can specify a fixed maze as a CSV file. So here in create maze function, I will specify that maze in load maze parameter. And here is the maze with 2 hurdles and the cost is shown as 10. The hurdle cost is not yet considered, and this cost 10 is actually this path, which is the shortest path between start and the goal cell. Now let's include the hurdle cost as well. I need the position and the cost of each hurdle. So here I can generate that information from the variable length input argument h, which is tuple inside the function. So for each hurdle in tuple h, I will pick the position and the cost value as inner tuple inside this hurdles list. Then over here, after adding 1 in the cost, I will check all hurdles inside the hurdles list we created a while ago. If the position of the hurdle is the current cell, which is the first element of the tuple, it means the current cell is the cell with hurdle, so we will add the cost of that hurdle, which is the second element of the tuple. Now the cost is 1, 4, which is basically this path. So this time the algorithm has not considered the path with the hurdle because of the high cost. It's important to view the path in simulation as well. So let's do that on the similar way we did for the graph by first calculating the reverse path. So here is the empty dictionary. And over here we will add the key value pair inside the dictionary. Outside the while loop, we will invert the path dictionary to get the forward path. We will get that as a dictionary as well, so the forward path is also a dictionary. And starting from the goal cell until we reach the start cell, we will pick the value from the reverse path and will make that as a key of the forward path dictionary. And value of forward path is the key of the reverse path. Then the next cell and so on. We will return the path as well. Now I will trace another agent on the above calculated path to see its movement on the path. Color will be cyan. I will make the argument field equal to true to have a full size agent. And I will make the footprints equal to true to see the complete trace. Then in the maze class we have a method trace path to simulate the agent movement on a path. As input argument we pass a dictionary with the key as the agent and value as the path to be traced. We have 2 hurdles added. And now you can see the agent following the path with a total cost of 14, which is not the shortest in terms of length or the number of the cells, but shortest in terms of cost. Let's just make the cost of hurdle 1 as 0, so effectively that hurdle is not there. And now the cost of the path is 10, and if cost is 100, you can see the different path. Let's add 3 more hurdles. Now is this path which has 1 hurdle because there is no better option, and hence the best cost in this case is 110. Now let's make the function more general, in a way that any cell can be the start cell instead of just the last cell, and any cell can be the goal cell instead of the cell 1, 1. Goal cell is the property of the maze that we can select while creating the maze. For start cell, let's add that here in the function with a default value as none. So if we do not provide the start cell, its value will be none. And inside the function we can set that value to the last cell of the maze. So if none, the start cell will be the last cell, and otherwise it will be the cell specified. We need a couple of changes inside the function. Over here, instead of the fixed start cell, we will specify that as the start cell variable. Then here cell 1, 1 is assumed to be goal. We will change that to underscore goal parameter of the maze. Similarly, we will change this one to underscore goal and here too. And over here it will be the start cell variable. And that's it. Let's check it. And it's giving the same result. Now here instead of the fixed maze, let's check it for a different random maze. Let's change the goal of the maze as well to cell 14 and loop %100 means there will be multiple paths. Now here while using the Dijkstra algorithm, let's change the start cell to some other cell, for example cell 61. And so then agent should also be placed at 61. Let's check it. And there is error. It is about the positional and keyword arguments. The keyword arguments must be passed after the positional arguments. And now you can see a different start cell and the different goal cell. Let's change the maze size to 1015. And now this is the path with the minimum cost of 18. You can test it for different size and patterns of the mazes, which are discussed in the starting video of this series, and the link is given in the description. So that's all from this video. If you find this helpful, please hit the like button and also subscribe to my channel. Moreover, see the other contents related to Python programming, PLC programming, machine vision, sensors and instrumentation etc. available on the channel. Thanks for watching.